Okay, looks like maybe people are done trickling in. So I'll just reiterate what Norman said. This time, how we're handling questions is we're going to ask that you save them until our scheduled Q&A periods on the schedule. There will be a Q&A period after my introductory talk. That'll be 15 minutes, so we have quite a bit of time to talk. And the reason for that is because we want to use that period also for any of you who might be interested in collaborating with us. We just want to get to know you and your interest in the project, as well as answer any questions about my quick recap of what this is. So with that, I'll get started. So, oh, that's weird. Okay, so I don't know what the slides look like for you, but for me they look a little weird, but I guess that's okay. I don't have two screens to separately have the meeting and the presentation at this time, so it's a little bit more awkward than usual. But yeah, so the project that we've been working on for the past 3.5 months is understanding trust. So we're using a particular mathematical operationalization of trust, which is that if you have one agent moment, which we'll call agent 1, and another which we'll call agent 2, then what it means for agent moment 1 to trust agent moment 2 is that agent moment 1 doesn't want to take any manipulative actions that interfere with how agent 2 makes decisions. So the reason I'm calling these agent moments is because the kind of the main case that we think about is the same agent over time, and does it trust itself? And so the way that we're thinking about these manipulative actions in that case is they are like self-modifying actions. So if agent 1 is an AI agent and agent 2 is that same AI agent later in time, then the question is, does agent 1 want to modify its source code so that agent 2 is making decisions in a different way? In which case we say agent 1 doesn't trust itself. So yeah, this is a relationship between agent 1 and agent 2 that like given the nature of agent 2, does agent 1 want to interfere with how it makes decisions, or does agent 1 trust the way that agent 2 makes decisions? Note that this is about justified or rational trust, not whether we can hack something together which chooses non-manipulative actions, but rather whether we can create a perspective that looks rational to us from which we can choose these non-manipulative actions. So there's 4 main motivations for this. There's humans trusting their own future self, which you could call rationality. There's the AI trusting its future self, which you could call stability. There's humans trusting AI, which you could call alignment. And then there's AI trusting humans, which you could call corrigibility. That probably requires more explanation, but I don't have time to go into it. So we focus on the case number 2 of AI trusting its future self, mostly because this is the simplest case. So we can analyze a system of our own designing and say, does this system trust its future self? And also because this is kind of a prerequisite for alignment. If we have an AI system that has some kind of safety story, then that safety story had better be stable. That is, the system doesn't want to modify the features of itself that contribute to that safety story, or else it's not a very good safety story. A critical methodological assumption that we're making is that we're interested in agents with bounded computation because realistic agents have to have bounded computation. And so we don't want to assume that it can solve like arbitrary math problems or logic puzzles. And as a consequence of this, we don't want to assume that it can think about its own decisions arbitrarily far into the future. Like if you imagine that a situation is well described by some sort of game tree, we don't want to assume that the agent can play out the whole game tree in its head. Therefore, we want our proofs about trust to respect what's called the Vingian principle. This was first articulated by Eliezer Yudkowsky. The Vingian principle just means that we can't assume that the agent can predict its own future actions. The Vingian principle is what differentiates reflective consistency, which is the subject of our study, from the more commonly studied notion of dynamic consistency. So, whereas dynamic consistency asks, would you endorse your own future decisions if you knew what they were? Reflective consistency asks, can you endorse your own future decisions in ignorance of what specifically they are? So dynamic consistency gets at the concept of consistency of preferences across time, whereas reflective consistency gets at the notion of consistency between how an agent makes decisions and how it would prefer to make decisions. So it gives us more of a notion of consistency of a decision theory. But we will call reflective consistency tiling for short. So the reason we call it tiling is because we just have this picture of like an agent architecture that can tile across time without kind of interfering with itself. So you have this trust relationship of the agent with itself across time. Previous work on reflective consistency has studied decision-making via logical reasoning, but not probabilistic uncertainty. In particular, we're going to take a Bayesian frame on how probabilistic uncertainty works. The broad plan is to combine dynamically consistent decision theories with a Bayesian theory of this computational uncertainty. And so the general project structure has these two parts, and the goal is to combine them together. The first part is tiling proofs which look roughly right, but which don't explicitly spell out how the computational uncertainty should work. So maybe we make some plausible assumptions about computational uncertainty, but the tiling proof sketches don't come with a constructive view on like, here's exactly how computational uncertainty works. And then the second part is these computational views of how computational uncertainty should work, where we actually construct a thing that is reasoning in this computationally bounded way. And this is all inspired by logical induction. And so the project is to try to get these two things to fit together into a coherent whole, which would give us a proof of a reflective consistency for a constructively specified computationally uncertain agent. the schedule of the rest of the talks through the course of this this morning for me, or whatever time zone you're in. So there's this talk, and then we're going to have a Q&A discussion. Then kind of the first block of talks will relate to that first block of things. So Norman will talk about an improved tiling proof. Paul will talk about some difficulties with our formalism, and Hannah will discuss some attempts to improve the formalism that we're working in. Then the second block of talks will relate to that second piece. So Paul will introduce Bayesian logical induction. Roman will present a new construction for Bayesian logical induction. And then finally, we'll have our second question and answer block and time for discussion. So yeah, that's it. And now we have some time for Q&A and discussion. Mateusz?
Yeah, so how would distinguish? So I'm imagining a situation where agent moment 1 takes some action, but then enables agent moment 2 to take some other action, such that these two actions in combination are like optimal utility for both of them, but that if the agent moment 2 took this action on its own, then this wouldn't be a good idea for either of them. So basically like something like a sequential Pearson dilemma thingy. So in this case, agent 1 acts so as to influence the action of agent moment 2, but I think you wouldn't want to rule it out as, trustless.
Yeah, so I guess concretely, we're currently focusing on the case where the utility function is shared. Of course, we would like to generalize beyond this, but that means there is no ability to set up a shared prisoner's dilemma like that, because like you do have coordination problems. Coordination problems are a big problem for us, but so long as agent 1 sets up a situation where agent 2 is able to take the action that coordinates with what agent 1 has done, and agent 2 knows that agent 1 has taken that action, then we can coordinate. So I guess in my way of thinking of it, if there is a prisoner's dilemma like that, then I would basically count it as lack of trust if it's like agent 1 has to manipulate agent 2 into cooperating in a prisoner's dilemma. So it's kind of I guess it's kind of a question of what counts as manipulation, right? So in the formalism that we're working in, we basically just declare, well, these things count as manipulation and these things don't. So we just kind of know it when we see it. And so if there is some binding that agent 1 can do on agent 2's actions that you consider to be a cooperative kind of binding, where you set up some kind of pre-commitment mechanism to stop defection in a prisoner's dilemma, then you could just, if you wanted to, you could just count it as not being manipulative, because we don't have any definition of what counts as manipulative. We're just declaring certain things as manipulative or non-manipulative. But in my way of thinking, I wouldn't do that. I would say that it does count as manipulative, and what I would want to see in order for something that I would call it like a trust result would be that the decision procedure is such that it can, of its own free will, without any binding mechanisms, decide to cooperate in the prisoner's dilemma. for example, if it's like EDT and it considers it's like agent 1 and agent 2 consider their actions to be sufficiently correlated, then they could cooperate. That would be the kind of reason that I would more be looking for in these sorts of proofs. Steve?
So I guess, oh, sorry. Can you hear me?
Yep.
Okay. I'm interested in this idea of rational and justified trust, and I'm just trying to guess to myself what you mean by that. Like one guess might be, well, A1 by the light of its own utility function shouldn't manipulate A2. But then I think, well, that's something you could hack together. So then maybe the idea is start with the utility function and then get, like you could hack it together because you could build the utility function in the right way or something. Is that, I mean, so, but maybe if you start with the utility function and then you want trust, is that what it is to be justified?
I think that the way that I'm thinking about it is we want to spell out the conditions for a trust theorem, right? Like we want to consider what the general conditions are. And then some ways of satisfying those conditions might be hacked together. Like agent 1 simply values non-manipulation. Like, fine, yeah, that's going to satisfy conditions of a theorem pretty plausibly, depending on the theorem, of course. And it's just going to also look hacked together. But we want like as broad of conditions for such a theorem as we can get, so that we also include things that are not hacked together in this way.
But I mean, is the idea of shouldn't manipulate to do with by the lights of your own utility function, or like what makes it justified trust?
Yeah, I think what makes it justified trust is that we can spell it out in a rational agent framework. Like, it's okay if it's hacked together in that way, of like the agent simply prefers to not take manipulative actions. We wouldn't want to restrict to that case because that seems too artificial. We want like as broad and illuminating of a trust theorem as we can get. But if it's within a rational agent framework, then I think it's fine from the perspective of like what I meant by rationally decide to trust. I want like what I'm trying to rule out there is people coming up with a decision procedure specifically for the purpose of like winning at this particular decision problem, but that decision procedure doesn't look rational in general.
So what do you think about the idea that, look, it should be that you can build trust around a utility function rather than vice versa? Is that the same thing? Like the hacking sounds like it would be start with the trust problem, then build the utility function.
I think it's not exactly the same thing, but it does feel very related. It's like, yeah, I want the trust theorem to be such that for like a broad class of utility functions, the agent can trust itself. I should say I want the trust theorem to be about a decision procedure that has the property that for a broad class of utility functions and a broad class of decision problems that the agent could be in, we don't really distinguish between those two things very much in this formalism, but like, yeah, it shouldn't be the case that we get trust specifically because we have this term in the utility function that's against manipulation or something like that. That would be unsatisfying. It seems like for the right decision theory, most utility functions, unless you specifically prefer to manipulate yourself or something like this, like as an agent that exists over time, you should by default be on your own side in a way that makes you trustworthy to yourself. Yeah, cool.
Okay, so I think this this problem of dealing with computational uncertainty in decision theory is super interesting, and I've kind of been convinced that maybe you have to go a little bit beyond the IXE framework for this question to make sense. So I do have some doubts about whether kind of being Bayesian about math on a like core level is ultimately ultimately a good idea, you know, related to pre-commitments. But if you know, if this can be overcome, I think that's awesome. But my main concern about about working on the research and myself is that maybe the kind of interesting mathematical questions are so seductive that I end up getting spending a lot of time doing you know, logic, studying like recursion theory and stuff, and maybe it's not the fastest route. So what I'm wondering about is like, how do you see this obstacle as kind of kind of being a necessary like bottleneck? Like in my mind, what I want agent 1 to trust agent 2, what I have in mind is that agent 2 kind of like cares about some endorsed version of agent 1's utility function, or like or that agent 2 is sort of a more rational version of agent 1. And what I can see how potentially some logical uncertainty issues arise when trying to define that statement rigorously, but I'm wondering if you have some if you could go into some sort of more detail about how you think this happens. Or does this question make sense? Like, could there be some simpler route where I say, okay, I will simply study the preference ordering of agent 1, and I will try to talk about how agent 2 can respect that preference ordering in a way that completes it in a sort of a trustworthy fashion.
Yeah, so I mean, I should say I'm happy for anybody else to jump in with thoughts on this one. I guess my thought is kind of, I could imagine working on this kind of preference ordering perspective of like I'm guessing that what you're imagining is something like agent 1 is a more irrational agent and agent 2 is a more rational agent. So there's been some like reflection that has happened, but rather than coming up with a theory of how that reflection works, which would be a theory of computational uncertainty, like a theory of how you can start as this very like incoherent agent and become more and more coherent over time. What you're suggesting is instead we just take the perspective, like instead of taking the perspective of agent 1 and figuring out how it can like evolve into the perspective of agent 2, instead we just take this perspective of agent 2 from a less bounded perspective and say like, well, how can we respect the wishes of agent 1 even though those wishes are ill-defined?
Exactly, yes.
Yeah. And I guess I think it's worth trying, worth pursuing, but my own take on it would be that handshake kind of needs two sides. Like, in order to validate a method that you like, say you come to me with such a solution, you're like, okay, here's my way of agent 2 respecting the incoherent preferences of agent 1 in a coherent manner. Then I want a story where like agent 1's reasoning about that gives agent 1 reason to trust agent 2, right? That's kind of the perspective here, is that trust has to, like, you have to take both sides into account. So I think there's a lot of failure modes around like agent 2 kind of paternalistically saying, this is like better for you, I know better, I'm going to make you better off by my own understanding. And the kind of worry is that that doesn't in some sense really respect agent 1's preferences. And then the goal is to show, by virtue of like the way that agent 1 reasons about agent 2, that a particular proposal in this respect actually hits the mark.
Yeah, I really like the reframing. I'm kind of thinking of things from the agent 2 to agent 1 perspective, and you kind of need both directions. But I think that makes a lot of sense. But I still have, I guess maybe a crisper way of kind of explaining the doubt is, is the hardest part of resolving agent 1's inconsistent preferences actually its logical uncertainty, or is it just the case that that we kind of don't have kind of fully consistent preferences, and we can't necessarily work that out by, like, if you locked me in a box and gave me 1,000 years to think about my preferences, I'm not sure that I come out with an endorsed preference ordering.
I guess what I would say is something like,
save this question to the second Q&A session.
oh yeah,
Like
I guess
after
that's
the logical computational uncertainty stuff has.
yeah, thanks for noticing.
And yeah, and meanwhile, I guess if anybody, like, we've received some information that like there are some others that would probably want to join the group, and if you any of you would like to provide some thoughts about the agenda that Abram has presented now or later. Okay, hi, Ben.
Yeah, so I just wanted to ask about a topic that I'm kind of interested in, which is value uncertainty. So I'm wondering if there's been any work done on trying to incorporate value uncertainty into this picture, if that's something you guys would be interested in exploring, like what that might look like having an agent that is not only like computationally bounded or logically uncertain, but perhaps also uncertain of their values, and whether it might be possible to still obtain tiling results in that situation.
Yeah, to
And
me
I guess
that's
trying to synthesize
100%. Yeah, 100%
Sorry, go
on the agenda. I've got I have a lot of thoughts on that. I have like a talk that I could give on that. Maybe like one of these Thursdays I'll give that talk, or maybe several of those Thursdays if it ends up getting broken up into longer than this time period.
Great. I'd definitely be curious to hear more about that. Because yeah, that's something I'd be interested in exploring as well, and also interested in looking at like ideas that have been proposed for managing moral uncertainty in like the philosophical literature, and whether we can like formalize those and adapt them to like a more sort of general agent context, and see which ones might be like reflectively consistent, for instance. But those are just sort of some ideas I've had, but yeah, happy to discuss that more later, because it sounds like there's a lot that could be discussed there.
Yeah,
yeah.
My general perspective on this is like, we want to make these trust theorems more and more practical and applicable to the actual situation we're in, and value uncertainty is a big part of that situation. The fact that humans can't just like write down what our values are. And so in order for these type of theorems to apply to actual AI safety, we really, value uncertainty is one of the critical aspects that the theorem would need to account for.
All right. Let's move on. So now we will start the cluster that Abram described about like the sort of the proof sketches for reflective consistency that do not yet incorporate computational uncertainty. And I will first give a presentation about a theorem that we proved during the camp that's like currently our most sort of refined version for this. So yeah, and I also want to use the the theorem through the process to illustrate how we generally construct formal proofs for tiling. So hopefully that will like answer Steve's question a bit about like how is trust actually justified. So the setup, for the setup we consider a very simple framework where we have an Joe, a name I made up for our agent, which is essentially a decision algorithm. And by this we mean that it constructs Joe like throughout its like operational lifetime constructs some policy which which says what actions he will take in response to certain observations. And since we're not like assuming that it's not reasonable to assume that Joe knows the policy from the start, we are imagining a picture where it's constructing this policy while it's encountering these observations. And for these several tiling theorems, the final one of which is like the one I'm presenting today. Like there's some prior work done by Abram and his previous mentees that led to this, and we're all considering tiling under the so-called updateless decision theory, just because like that's currently the only framework in which tiling theorems could be obtained. And for this decision theory, the agent basically takes the expected utility with respect to a fixed prior and makes the decision based on like which action in response to the certain observation maximizes the expected utility. And notice that it's a point-wise maximization, meaning that we are not conditioning on the full policy, but just one policy point. Oh yeah, by the way, this an observation action pair is a policy point. Yeah. And so now we proceed to formulate tiling. So if, as Abram said, like if agent moment 1 trusts agent moment 2, it means that it wouldn't need to modify any part of the decision or decision making of agent moment 2. So to like formalize this, we have to introduce what kind of self-modifications that we're considering. The modification that we're taking into account specifically for the theorem I'm presenting is a very simple kind. It just takes one response, like a self-modifying action AM takes the response of agent moment 2 to some specific future observation and changes it. So and for this observation, for this policy point that this modifying action changes the action that's replaced that replaces into the slots has to be non-self-modifying, so that we don't have like chain of self-modifications. Later, Paul, actually right after me, will talk about like the issues related to this. And each self-modifying action has a non-self-modifying counterpart, which just does whatever the action is supposed to do. So the action actually has like some part like where you actually take a normal action. It's just like in addition to that, it's self-modifying, and the non-self-modifying version of that action just doesn't do this internal self-modification. And for tiling, tiling would simply mean that if the expected utility conditioned on taking a self-modifying action wouldn't be strictly greater than the expected utility conditioning on taking any non-self-modifying action. Taking like, sorry, wouldn't be greater than the maximum of the expected utilities conditioning on taking non-self-modifying actions. Now we introduce so tiling couldn't be obtained like in a vacuum, because as you can see, like self-modifying actions generally have more power. So we have to make specific constraints on the decision problem, and in our formulation, the constraints on the decision problem take the form of like what the agent believes about the problem. And there are essentially two assumptions in this category. So the first assumption, fine-grained fairness, says that the expected utility conditioned on a certain policy, a certain self-modifying action being taken is equal to the utility conditioned on the action just being the non-self-modifying counterpart of this action, and the policy already having the policy point that the self-modifying action is trying to change it into. So this fairness notion is intuitively means that you do not the environment does not intrinsically prefer you to self-modify. Like if you are doing effectively the same thing, like as if after you have self-modified, then you will get the same utility. The second assumption, which I think is the key to this tiling result, is action coordination. So this assumption says that this assumption is a bit complicated. So I decided to illustrate it by a specific example that popped up a lot, like while in our research discussions during the camp. So suppose that O prime here is the observation that the fridge in your house is empty and you need food, and A prime is the act of heading out to the supermarket. So like specifically like leaving your house. And suppose that the observation O is encountering a red light at the crossroads after you leave your house. And the action A is stopping upon seeing the light. Oh, okay. Thank you. And so this assumption says that if you take the action, the action of getting out of your house, maximizes your expected utility, and this should be equal to like the maximal, like the argmax action. So it essentially is saying that if you know that you are going to stop upon seeing the red light, then it makes sense for you to go out of your house. Otherwise, like if you are not maximizing your response to the red light, then you probably should stay at home. Otherwise, you might die. Yeah. So this is the sense of coordination that we're thinking about. And there are also some technical assumptions on the agent's self-belief, which I will skip due to time constraints. So assuming, making under these assumptions, we're actually able to prove that the agent has this tiling property that I explained previously. So now we just take a quick look at the proof. So if you let's assume that you take a self-modifying action, then the expected utility would be by fine-grained fairness equal to the right-hand side of this equality, and you could maximize by like definition of max. You could take all the maxes you can take here, and by one of our technical assumptions, this faith in joint argmax, this you could this joint maximum over two actions is actually could be decomposed in this way. Yeah, sorry, I don't have time for this. Yeah. And by the action coordination assumption, oh sorry, the weak is extra word. We could then simplify. So this this technical assumption is actually made to fit together with the action coordination assumption. We could simplify this joint argmax into like a single max. No, yeah, like using the coordination assumption here. And in the end, we just use the fact that the agent actually knows that he's using UDT to remove this condition that the agent is argmaxing over this action. And this is how we show that the agent does not strictly prefer self-modifying actions. Thank you, and sorry for the delay. And Paul will talk about effective policy next.
Can you see this? Oh, hello. Can you see this presentation now?
Yeah.
All good.
Great. Thank you, Norman. Now for the dark side of our UDT framework. I'm going to mostly skip the notation we use in the paper for the sake of clarity. Observations are circles, actions are squares if non-modifying, and rectangles if modifying, and by default, the action for an observation has the same color. Bottom and top, in the observation row here, are special observations, representing a logically impossible observation, like calculating that 5 is composite, and a logically certain observation, like calculating that pi is greater than 3. We represent a self-modification as being some observation-action pair, where the action has an ordinary component and a modifying component. The ordinary component is some object-level action, and the modifying component targets some other observation-action policy point, changing its action from whatever the policy used to dictate to whatever the modifying action dictates. You might recognize this as something that Norman talked about. Recall that in our framework, self-modification is to be avoided. This is for numerous reasons having to do with... Sorry, I didn't start my timer. There we go. Recall that in our framework, self-modification is to be avoided. This is for numerous reasons having to do with how we think about trust and updatelessness. Most notably, a predecessor agent should trust its successor agent, and an agent at an earlier time should trust what it will do at a later time. But self-modification means manipulation, and that means a lack of trust. Self-modification can also chain and produce undefined behavior. A priori, we have no reason to expect that an agent will stop at just one self-modification. And without the explicit regularity assumptions that Norman mentioned, elements of A sub m, the modifying set, again in this actions chunk, can have modifying actions whose modifying component sets the targeted action to be yet another modifying action. So you'll recognize that's what's going on in this second one. Can you see my cursor or no? Just to check.
Yes.
Okay, good. This second one here, where we have a modifying action whose prescribed modification will set it to be another modifying action, which is something that we've forbidden. A UDT agent could have picked any update list policy to use in the beginning, including non-self-modifying versions of the policy that the agent effectively ended up using. Self-modification means that an optimally updateless agent wasn't actually able to be updateless or optimal. And finally, reflective stability is just a useful and strongly motivated property of itself. That's the whole point of tiling. All right, so what if we try the obvious unrolling strategy? One process we might really want in order to do this is to take in an arbitrary UDT policy, which might have self-modification in it, and use that to output some effective version of the policy with no self-modification in it. This should be well defined with only one output for any given input, no matter the computational details in between. This should also result in something that mostly looks like the original modifying policy. It needs to do the same thing, except that it doesn't self-modify. And of course, physicality sorts of constraints apply. Here's the canonical naive idea to try, the obvious unrolling strategy, as found in some older posts and papers. What if we construct the effective policy by just running and removing all of the modifying policy points of the original policy? In the schematic notation that I've used here, that would correspond to replacing each modifying action with its left subbox, the color one here, and replacing the right subbox's targeted action with the new specified action. So here, it looks like the obvious thing to do is take the blue here, the blue observation, left subbox gives you new blue action. And since it says look for the orange observation and overwrite whatever its action was with the purple action. So we just get this. A more complicated case is near the bottom here, where we have a handful of different modifications, and we can just run all of them. Why not do that? What happens if we try? Unfortunately, that won't work. Part of my contribution to the project was a sketch of several ways that this natural seeming process can fail. First off, remember the bottom observation from before? This is why I introduced it. What if we have some policy points or branches which trigger on some iteration of bottom, and whose prescribed actions are modifying ones? They will never be chosen, but under the naive unrolling process, all such modifications will be enacted, possibly totally overwriting the original policy. And again, you can see here, we have these bottom observations. We have the modifying actions they prescribe, but we're never going to get there. And we've completely overwritten our starting policy with a totally new one. So that seems bad. All right, well, even if we forbid that, then race conditions can arise. We have two simple kinds of race conditions. First off, what happens if our two modifying actions point at each other? As we go through and unroll and successively make all of the modifications that the modifying actions prescribe, we do that in some order. And in that case, we're going to wind up only getting one of those two. We'll either overwrite the blue with green or overwrite the red with orange. And even if we say something like you're not allowed to overwrite a modifying policy point, we still end up with a more classical race condition where two different modifying policy points point at the same third one. So the order does matter here, whether we overwrite our green with yellow or with cyan. I know I'm slightly over time, but I'm nearly done. Finally, even if we get rid of all of those, we say things like you can't target modifying policy points, you never run anything that never actually comes up in normal operation, and for any given policy point, at most one modifying policy point can target it. then we wind up with these more tangled race conditions, where, for instance, we have some ordinary action that points at a modifying action. It'll eventually lead to this. The output of this pink action somehow leads to, we will observe the red observation. That leads into this red modifying action. And similarly for this azure pair, we have an azure observation and action, and that'll somehow cause us to see the blue observation and the blue modifying action. And once again, whatever we do, we're only going to end up actually running one of those two modifications as we do this stepwise. Either we're going to wind up replacing our pink with green, and that'll totally put us off track to ever see red, because now we don't do the thing that gets us red. Or similarly, we replace our azure with orange, and now we're totally off track. We'll never see our blue observation, so we don't run that one. And the reason we don't run those is that's now an impossible possible world. That's something that won't come up in normal operation. So it seems like this whole idea of trying to unroll to effective policy is in trouble. Over to Hannah for, before that, expanding the scope of an observation to include partial histories so that we don't wind up with even these tangled race conditions seems like a pretty tempting fix. But then if we adopt that, what do we make of decision theoretic setups like Sleeping Beauty or Distracted Driver, which in some central way depend on memorylessness? I'll let Hannah give you one possible fix.
So I'm going to present an alternative way of formalizing assumptions that lead to trust. Our starting point is the same. This is a decision procedure UDT 1.0 as in Norman's presentation. But instead of self-modifications, the agent sends its future self a message that is like not binding. So it's not like you need to do, you have to do this. It's just like, I think you should do this. And policy is now not just a function of the observation, but it's a function of the observation and the message is received at that point. And it originates from Scott Barabrand. Let me start with an example. Let's say the agent wakes up in a room and can choose between pushing two buttons. Then its memory gets wiped and it wakes up in another room and has the same choice. If it presses the same button in both cases, then it gets a reward, otherwise it doesn't. And in this case, it's very difficult for UDT 1.0 to cooperate, or like it we need a too strong assumption for this to work. And if the agent can send a message to itself that that you should choose the blue button, then that would be great. It's important that we don't want the agent to choose every action at the beginning, because of computational reasons. I just put here the UDT 1.0 definition as a reminder, and that the problem with the tiling proof is that the coordination assumption is, the previous tiling proof is that the coordination assumption is too strong. And instead of this coordination assumption, we aim for having just one weak coordination assumption that the agent understands the messages it sends to itself. Another advantage would be that the agent would still use this argmaxing rule, just taking into account the messages. But in the previous version, the self-modification was kind of artificial. Yeah, and the goal is to formalize this framework and find assumptions that that seem reasonable and lead to tithing. This is like an open thing, so it's not like Norman's proof. It's mostly just ideas. So let's start with the first attempt at formalizing this. So let's say the agent can send itself suggested actions. So it's like a very restricted language. The agent receives the observation and the message, and it chooses an action and sends a message. So yeah, you can see it here. Yeah, we can, well, O is observations, M is messages, A is actions, and M is messages. We can make this more precise, but it turned out that this is not the approach that we really want. Why not? So this refers back to Paul's presentation. We would like to handle self-modifications that are functions of actions. For example, if the agent chooses the right actions at multiple different observations, a self-modification will occur. And we want to handle stochastic self-modification because it is realistic that the agent might not know how things will work out. So a second attempt at the formalization that solves that addresses these issues is that for each observation we have a set of available actions. We have something called a message policy that for each observation there is assigned an action that it received as a message, and there is an enacted message policy that is the message policy that the agent ends up with. The policy is a function from the observation and from observations and messages to possible actions. The chosen policy is the policy chosen by UDT 1.0. So argmaxing over all actions. The effective policy is similar to the enacted message policy. So it's the policy that the agent actually ends up having after all possible self-modifications or interactions with the environment. And we could say that the policy is modifying if the probability of the chosen policy being different from the effective policies is bigger than 0. And yeah, so what assumptions would we need? I already mentioned the language coordination. We also want message fairness, meaning that messages are something internal to the agent. So the environment shouldn't encourage a specific type of message or something. And there's policy fairness that the environment should care about the effective policy, not the chosen policy. So one idea for this is that if the distribution on the effective policy is the same, then the expected utility is the same. And another one is that the utility and the chosen policy are conditionally independent. That's the end of my presentation.
Abram?
Yeah, should I get started on the second half or no?
Yeah, sorry, I was just trying to hit the applause and I hit the raise hand instead. Yeah, go ahead.
All right, thanks again, Hannah. Now to transition to the other half of our presentation on the topic of logical induction markets and Bayesian logical inductors. This is going to be a relatively abbreviated introduction to it because there's a lot to say and I've only got 10-ish minutes to say it in. The money pump or Dutch book frame, like I've presented here, is a common frame for justifying the value of Bayesianism and for analyzing the worth of decision theories. Briefly, if a system for reasoning or making decisions can get it so wrong that a reasonable adversarial agent can offer the system bets or trades such that the system accepts those offers and the adversary ends up taking all their money, then that's a bad system and we shouldn't use it. For example, the system might have non-transitive preferences, red worse than green, worse than blue, worse than red. Then an adversarial agent can take all the system's money for offering it a green for red plus $1, a blue for green plus $1, and red for a blue plus $1. And eventually the adversary will end up with all the system's money, as S happily pays A all of its money to trade around in circles. Logical induction markets and the Bayesian logical inductors built on them are grounded in this principle as applied to bounded rationality. By the way, I took some of these slides from Abram's lecture notes. Thank you, Abram. If you want to see the full notes, ask him or one of us from the EISC track after the presentation is complete. The basic idea of a logical induction market is that we want to apply money pump flavored criteria to relatively unconstrained reasoning systems. If we interpret the subjective credences of some reasoning system as prices in a stock or prediction market, then it should not be possible for simple traders running polytime algorithms to money pump that market. To construct a logical induction market, we specify a language L to express propositions in, along with a class of continuous trading strategies from the history of market prices of propositions to linear combinations of those propositions, which are the trade orders. The price of a proposition here is always between 0 and 1 and corresponds to the market's subjective credence for the proposition. We interpret positive coefficients on propositions as buy orders and negative coefficients as sell orders. But we're not actually done. We also need to specify a class of traders. For our purposes, we'll pick the class of efficiently computable traders, whose runtime to produce a trading strategy is, as above, polynomial in the number of days. Finally, we must specify the initial bankrolls for the traders. 2 to the negative description length is a popular one, and give a schedule for when each of those traders enters the market. It's important, by the way, and I think I forgot, right, class of continuous trading strategies. That's a fairly important point here for reasons that I won't get into because they're complicated and long. Then on each discrete day t, we can think of the following things happening in order. First, new traders for day t enter the market with their starting bankrolls. As time goes on, those bankrolls get exponentially smaller because the later traders will generally require longer descriptions. Next, any observations which resolve proposition prices, to 0 or 1 for instance, pin those prices as appropriate, and new propositions might become small and thus open for trading. By small, we mean that the proposition is short enough that some trader will have sufficient computing time to evaluate and trade on the proposition. All other propositions in L are considered large. Did I? No, I didn't in fact have that. Yeah. All traders think for slightly longer than yesterday as a polynomial function of t to generate their trading strategies. Oh, right, I do need to briefly go to this next one. To generate their trading strategies, and the house, metaphorically, sets prices of propositions such that the market as a whole is balanced. Equivalently, for the prediction market frame, the house sets the odds for betting on each proposition to equal the ratio of money on yes versus no. Finally, traders make their purchases based on day T's new prices, and each trader's wealth is updated from the previous day's wealth. The logical induction criterion is what's above here, and is our criterion for is this overall market structure, is the reasoning process that generates it a good one that we actually want to use. And that's simply that if the market we've described can't be money pumped by any polynomial time trader, that is, there's no way for any polytime trader to make guaranteed and unbounded returns from a finite stake, then this is what we call a logical inductor. And is something that we might find suitable to use. You might have noticed that the construction of a logical inductor is extremely underconstrained. In particular, nothing actually says that the trading strategies have to respect propositional coherence. The two rules for propositional coherence that we care about are that the probability of top has to be 1, and that if A and B is the same as bottom, then the probability or the price of A or B has to be the sum of the prices of A and B. And in particular, as Abram's put here, because the house rewards arbitrage of failures of these rules, a logical inductor will converge towards respecting these rules. Or alternatively, one way we can think about the difference between a general logical induction market and one which also has propositional coherence is that for a general logical induction market, a trader can in principle buy or sell any basket of propositions, however nonsensical that basket might be. So it could bet on P and then bet on some Q that's equivalent to not P somehow. By contrast, if we shift the basis so that if traders have to place bets on maximal size conjunctions of propositions and their negations, such that to trade on a single proposition, they have to spread that stake across many such baskets, this allows us to enforce propositional coherence directly, because the probability or the price of bottom has to be 0 by these coherence rules for one of several reasons. Here's a sketch of Bayesian logical inductors as Simon Eisenstadt presented them. They take this idea one step further yet. We can think of a Bayesian inductor as an extra module sitting on top of a propositionally coherent logical induction market, as we just discussed. Unlike the traders in the logical induction market, the Bayesian inductor has credences for all propositions in the language L, not just the small ones. At the end of each trading day T, the Bayesian inductor gets a list of prices for each proposition traded on by any trader in the logical induction market, the small ones, on that day, and performs a set of relatively simple updates based on the new information. For each proposition S that all traders in the logical induction market consider small, the Bayesian inductor directly sets its credence P sub T of S to the logical induction market's day T price for S, QT of S, and likewise for propositions that have had their prices pinned to 0 or 1, say, by observation. For large propositions, the Bayesian inductor performs a more classical update based on the prices on small propositions, adjusting its credences on large propositions to be coherent or locally invalid, in the sense that they now satisfy simple numerical constraints for logical connection and conditionality, with its new credences for small propositions. And I've provided a little schematic at the top here of what unrolling that process might look like, unrolling here in time rather than in the sense of what I was talking about before, and also provided Abram's part of the slide where he lays out the constraints that Sam Eisenstadt had provided for what exactly these blue processes, the overwrite and update, needs to satisfy. So for instance, for one, the overwrite is in 1, right? If there's a price to overwrite something with, we overwrite it. But this is not actually enough for what we need. There's a self-consistent choice that we could make, and we shouldn't be allowed to make it. We could set our Bayesian inductors module to assume that tomorrow's logical induction market prices will be precisely the same as today's with certainty. As detailed here. And as Abram wrote here, this is a very unsatisfying choice, obviously. Both I and Roman, who's up next, spent a little time working on other formulations of the no net expected update rule. This fourth one here. Right, balance this, sorry, not the fourth one, this additional condition that you can derive from these four constraints, and which causes us this slight weirdness problem, where maybe we can set our expectation for tomorrow to be identical to today. We spent, formulations of the no net expected update rule to both avoid the yesterday as point mass failure mode and conditionalization on probability zero events, as well as handling the space of price signals without having to compute an uncountably infinite sum, as the original formulation requires. I sketched out this this continuous or integral-based framework, integral-based version rather, that would work to handle real-valued coherence. And Roman detailed a discrete version that chunks up the interval into smaller bins, like so. And I'll give you a moment to have a look at this. And again, I'm not going to go into too much of what's going on here for time constraints, because I'm technically over time now. And with that being said, now for Roman to wrap up by talking about that work I've just mentioned. Roman?
Going to share my slides. So, today I'm going to talk about these beliefs about future beliefs. Notation for my talk right now is like we are going to have like I'm talking about like this Bayesian logical induction construction. As Paul mentioned, it is underdefined in the sense that we do not know how these beliefs about future beliefs are constructed. What does the market believe? What does Bayesian logical inductor believe about its own future beliefs? So the constraints. Sorry. The notation here is like we have a day of logical inductor, which is like the base logical inductor, like the one on which Bayesian logical inductor constructed on. On the day n, we have set of small beliefs, which is the ones that are touched by market. We also have the level of discretization, so we have so beliefs are can only be inside of the set. The Bayesian logical inductor is denoted as P. The just logical inductor is denoted by Q. So here are the logical inductor criterions, which Paul already mentioned. So first three could be just enforced because like what they are like talking about like arbitrary things we are just postulating, like Pn of phi could be just we could just set it to be. This is also could be just set to be, and this is also could be just set to be. And like the 4 and 5 should be it's a bit harder. It must balance some equation. So this and this construction should balance this equation. So we are now we now have to construct it. Also the condition which Paul did mention is this one, that the beliefs about future beliefs should sum up to one. Which means that we need to we will believe something. It just follows from probability theory. We will believe something tomorrow, and like with probability one, it will end up as some belief. So you to have a mental picture for beliefs, future beliefs, as a point in some lattice. So here is the multidimensional space of beliefs. P, psi, and theta is it's not perfect. Phi, psi, and theta is a small beliefs. So you is some possible belief of about this about how will we believe in those small beliefs tomorrow, for example. So you can believe that. This is just the point. So this is just the amount, the actual probabilities with which we believe those beliefs are just coordinates in this multidimensional space. So this lattice is like the space of all future beliefs. The super belief is like the probability distribution over this this space. So the more massive the point is, the more probability mass we attribute to it. So like it's like this probability distribution, the Pn of Qn plus 1 equals to this Q. So this Q could be anything from those lattice points. They are lattice points because we have some level of discretization. So the natural way, so the natural way to the first that comes to mind to assign this super belief is to have this delta super belief, where we believe that we will believe the same as we believe today. This introduces some problems, because first of all, because it is wrong, we will not believe today as the same thing as we will believe tomorrow. Also, there is a problem of updating from zero. It just contradicts Bayesian reasoning, and also because of the way we describe because of the way we define Bayesian updates, we will inevitably divide by zero, which is undesirable. That's why I also introduced this one more requirement that, well, this belief about future belief, this super belief, shouldn't attribute zero to any state, to any possible state, to any possible lattice point. So I those super beliefs as vectors. So each possible lattice point is a coordinate. We have this S-dimensional space with the discretization level D. So we have D to the power of S possible lattice points, which each has some probability value. So super belief is some vector. We have this linearity property that we can add those super beliefs and just point by point. Each value adds each value by point. So we also can introduce the norm of the vector. That way, this condition, which just follows from probability theory, distills to this nice form. And we also can introduce Einsteinian convolution, which I postulate to be when we have this distribution with the super belief vector, it attributes like we can like condense it, compress it to, we can like ask it, what is the average belief in this particular statement, for example, psi, and it will just average all of its beliefs. Like each lattice point attributes some beliefs, and we also believe in that lattice point with some amount. So when we average it out for some specific belief, like phi, we get like the expected belief. And expected belief tells us that it should be the same as belief in the day, in this day. So just the equation of like not the condition for the no net expected evidence, or like not net expected change in beliefs. So we just it condenses into this ninth form. We also have like for norm and for these convolutions we have linearity. So the way, so our task is to construct this vector f, this super belief. We can try, like my approach is to make it like to have a basis of those like basis vectors, which will linearly combine in the way that it will satisfy our conditions. So this is just the notation of it. So the basis should look like something. So for each belief, we will have some basis vector. This is actually this is just stipulation. This could be done in other ways. You could build all other kinds of bases. This is just what I propose. So I propose that like for each belief, we will have some special super belief that believes in this belief like differently, and all other beliefs the same. So it will be uniform for other beliefs, but not uniform for this special belief. And each belief, each like small belief, will have its own basis vector. Then, like we can like construct. So this is just a bit of linear algebra. No need to worry about it. We will. We can construct like this convolution matrix, which is so belief and each basis vector. We can construct this coefficient. So like this is like probability of n by the n of tj. Like so this is this equation. So this equation. So this vector f is decomposed like into the linear combination for like the coefficient to the basis and the basis itself. So when we like unfold it, we see that it's just matrix multiplication of these coefficients and convolution matrix, which is constant when we pick out a specific basis. So the solution would be just inverse matrix times this vector of probabilities on the day n, and like then we get those coefficients, and then we get the super belief vector. So this is just a general approach. You can try to like set out different bases, different like this will result in different convolution matrices. It needs to be defined, like it needs to be invertible in order for that to be the case. I suppose like like my proposition is to have like this maximum entropy approach. If you try to like, so we try to disperse this delta belief into like more like dispersed belief, and try to do it in maximum entropy way, you will result in something like exponential distribution over those beliefs. So this is like my proposition. The matrix will, in the limit, approach something like this, and it will be invertible. So this is like the equation for the basis vectors. So this is like the coordinate. This is the index of the superbelief. This is a bit complicated, so I don't kind of have the time to explain all of this. I'm already over time. Missing details. Figure it out. We need to figure out the specific like. I didn't mention how discretization all plays out in it. So we need to like the discretization needs to be finer and finer with each day, and I haven't actually talked about it. We also need to talk about edge cases, because if at some point the market believes that some proposition with probability 1, we can't actually force the future belief to be dispersed, because like to have an average without which. So if you attribute some probability to this belief being less than 1, then on average it also be less than 1, and so you can't satisfy this condition, this one. So you will attribute 0 to beliefs which attribute less than 1 to this particular belief. So the problem. Also, I haven't talked about normalization. Also, it could be added as some equation, but I haven't actually properly spelled it out. We also, 0-1 boundaries. Also, additionally to normalization, you need to carefully look out if your beliefs are actually out of 0 to 1 boundaries, and also you could possibly incorporate more equations with more bases, with longer bases. So people respect some small beliefs about future beliefs. So at some point, the market will start to introspect, and we will have some small beliefs about future beliefs. And you can see on the slide which kind of like future beliefs it could be satisfied with. So you could also take some equations from there and add them into like this set of equations here. So this is just like actually a set of linear equations which I transform into matrix. So yeah, sorry for being over time. Thank you for attention.
Okay, thanks everyone for staying up to this point. And so I think this is like a long session already. So so for myself, I could stay until like the next o'clock, like around half an hour or so. So if you like have questions, feel free to ask. And like if you want to take some refreshment or something, you could always come back like in the next 30 minutes or so, and we'll still be here.
I wanted to mention, I probably should have mentioned this earlier, that my plan is to have this recording edited and then post it to YouTube with the rest of the videos. So I hope that's okay with everybody. I guess a couple of other things to mention. So yeah, the rest of the recordings are being edited and will be posted to my YouTube channel. So if you want to get up to speed with everything, then watch out for those. And anybody who would like to be involved in this project, or at least hang out with us at some point, is welcome to come to these meetings. We are planning on continuing the Thursday meetings on this same schedule, at least for a little while. And if people are not already in the Discord that we're using, we can add you to that so that you can discuss things with us about this project. And yeah, maybe that's all for those kinds of announcements. I'll try and find my YouTube channel to link to it.
Okay. Now, I guess one way we could do this Q&A session, since there are like many presentations, is that so first, if anyone has like a general question that's not specific to any presentation, you can ask now, and then we'll go through each we'll ask if there's question for each presentation. And for Hannah's presentation, she has to leave earlier, so there will be no Q&A. Sorry. So now, are there any general questions? Oh, okay. Okay. You're right. Yeah. Okay. Then no. Anyway, I can still run through it quickly. Like, are there any questions for my presentation? If you still remember. Okay. Yeah. If there are none, what's the next?
How about for mine, for either half of it? We're skipping over Anna here.
Well, I have a question to Hannah's presentation, but since her presentation was somewhat closely tied to yours, maybe you will be able to answer.
I can at least try. And by the way,
so,
I'm glad that. Oh, go ahead.
So I didn't quite get how the communication between policy points is supposed to solve these problems, and the way I can make sense of it is something like each policy point, when it's trying to make a decision on an observation, is kind of trying to simulate what other decision points would do, what other policy points would do, and then take an action that has the highest expected utility, having considered everything that these other policy points would communicate. Is this roughly right? And if not, what's the right explanation?
Yeah, I don't think I can really answer that question for you. This is something that seems pretty core to what Hannah was working on. I don't know if Abram has a better sense of how those meant. Go ahead.
I think I should be able to answer the question, but I don't think I quite understood it.
So how are messages? How is message passing between policy points supposed to fix the problem of the problems that Paul presented in his first presentation?
Yeah. Okay. So the idea with the messages between policy points, like the core idea for me is, so we assume that in the decision problem, there's going to be some kind of self-modification channels, right? Like there's some ways that we can act, which would cause ourselves to be rewritten in some way. And those are, as Hannah mentioned, we want to allow them to be stochastic. We want to allow them to depend on multiple actions rather than just one action. But the critical thing is like the messages kind of run exactly parallel to those. So the assumption that we're making is that anytime the message, anytime we can self-modify, we could instead choose to send ourselves a message that's like, hey, you should do this. And so this is kind of a certain limited form of memory that's like, I remember that my past self wanted me to behave in this way or in this other way. That solves, like, it doesn't solve every coordination problem. We might still be stuck in some coordination problem with ourselves, but the idea would be that it allows us to solve any self-coordination problem which we would otherwise be tempted to use self-modification to fix. So if we have a way to fix some coordination problem with self-modification, we can instead solve it by sending ourselves a message.
Yeah,
I think that
that
didn't
makes
quite
sense.
answer your question. So, like, you're
No, I think you did answer my question.
oh, really? Okay, nice.
For my part, I'm not actually entirely clear on, first off, how the messages are supposed to work as far as targeting goes, because there's this implicit sense that Hannah brought up, and she's not really here to defend that, of sending things to the future instead of obviously the past. But I don't know that we have a sense of time here. And the other part is it's not clear. I mean, I guess it's less of a problem. The other thing I was thinking about, the fact that you can receive, you have to receive exactly one message. There's no allowance for maybe you don't get one, and there's definitely not an allowance for maybe you get more than one. I don't know how much of the problem that presents, though.
I think that the receiving 0 messages is easy to handle because we can just consider there to be like an empty string message. But multiple messages, we kind of really have to rule out, I think, because if one piece of me, like one of my past selves tells me to go left and another one tells me to go right, then what do I do? As for time, yeah, my idea during the course of this project has been updateless decision theory kind of spiritually wants to be timeless in the sense that Wei Dai's idea was really an evidential decision theory. And so he didn't want to assume some causal structure. He wanted it to just be probabilistic reasoning. And so I've kind of projected that onto the formalisms that I've proposed, and also like Hannah, like, I think there is this big question of causality of like, yeah, it seems like you could modify your future self, but it doesn't seem like you should be able to modify your past self. However, I've delegated that to the decision problems to sort out. Like, a particular decision problem offers specific self-modification opportunities, and I just think of the decision problem as being the one with the responsibility to make sure those causally make sense. So I think that is kind of a drawback at times, like possibly to reason about self-modification, we want to reason about causality more directly. But so far, I haven't been convinced that it's like a critical problem.
All right,
Though
thank
certainly
you.
it leads to some problems, as Paul has raised. Cool.
And by the way, I'm Abram and not Dish. I'm glad that you approve of the notion that I picked there.
I just have a question about the logical induction kind of motivation. So so it makes sense to try to avoid Dutch books, and if you want to take runtime into account, then maybe avoiding polynomial time Dutch books makes sense. It's, I guess, sort of related to like sometimes in average case complexity, you assume that the distribution is polynomial time sampleable. So maybe there's some sort of intuitive connection there. But I do wonder, like, is this really like getting you what you want? Like, you could instead say that you want some sort of polynomial time algorithm which has the lowest possible like degree of incoherence, or can't be Dutch booked very badly, instead of assuming that it's against polynomial time adversaries, you could just constrain yourself to be polynomial time, and then try to sort of have the best possible kind of degree of coherence. And I guess there has been some work from like Teddy Seidenfeld on measuring degrees of incoherence by and other kind of philosophers measuring degrees of incoherence by how badly you can in principle be Dutch booked. So I'm just curious about like the motivation of polynomial time traders specifically.
Yeah. So I guess first I should mention, like, I see polytime as a parameter of logical induction. We could pick other classes, like whatever we like. But like the real critical thing is just we have some complexity class of traders which we have these guarantees about. And so with respect to this question of, well, what if we instead make ourselves a polytime algorithm and then ask for certain guarantees, the way that I'm thinking about it is basically like, I think you want the same thing, like you want some kind of regret bounds to bound like how badly incoherent you are. But kind of the point of logical induction is like the algorithm itself is doing the optimization to make sure that you meet that regret bound, instead of like imagining some more intelligent entity that optimizes you to figure out what the thing that has low regret bound is, right? So like Vanessa Kosoy considered a framework, I think like the optimal estimator framework or something like that. I don't remember quite for sure, but where instead we have this, we imagine this like super intelligent optimization or like logically omniscient optimization for a small oracle, that then given access to this oracle, you can have these nice bounded rationality guarantees. And I find that kind of approach dissatisfying because it's like, okay, well, yes, you've constructed some boundedly rational entity, but the way you've constructed it fundamentally requires a superintelligence, right? Maybe you could say, oh, it's fine because like the way that people make artificial intelligence these days in practice is you have a super long training run that in some sense is super intelligent in comparison to the final product that comes out of it. And so maybe Vanessa Kosoy's framework is like a model of that. I could kind of see that kind of justification, but from my point of view, it's preferable to have the algorithm itself be doing the thinking to make sure that it has the bounded loss. And logical induction having kind of a higher complexity class than the type of thing that it's proof against, like it's proof against these polytime traders, but the algorithm itself for logical induction is not polytime, is kind of a consequence of that. We can also do some formal work to kind of brush that under the rug. I believe there's a way to formulate logical induction such that the traders are the same complexity class, but I don't know, it doesn't really fundamentally change the picture of what's going on.
Okay, so you're saying you like when I hand you the logical induction algorithm, what you would do is try to find regret bounds against polynomial time algorithms. So let's just have logical induction do that itself. But I'm not sure. Yeah. I guess it is questionable whether regret bounds against polynomial time algorithms are something that makes sense to look at for an algorithm that's not itself polynomial time. Like if you want kind of like this kind of mixture of expert type regret bounds, then you would probably want to say something more like that you're best in class, right? So in some sense, it makes more sense to me to just say I will be polynomial time and then I kind of can maximize my worst case performance, and that's sort of what the degree.
So as a sort of conjecture, I would say like, well, if you want something that's polynomial time that's similar to logical induction, it's still not going to be best in class. It's going to be like, it's going to have regret bounds against Dutch books that are like an even lower complexity class, like log time or something.
But I mean, maybe you could say, like that I allow that I will be exploited to some degree, but I try to minimize the rate at which money can be pumped out of me as a polynomial time algorithm by anything, like no assumptions on the
Well, you can't minimize against everything, right? Like, if there's no assumptions, then we have the thing that just knows all the right answers. And so
No, I guess what Cole is trying to say is like not look at the total, but like at the first derivative. So like the speed at which you are getting exploited.
Yeah.
And this is actually haven't like touched by us or logical induction. So the regret is unbounded, but the speed of regret is bounded.
Yeah.
I feel like in order to bound the speed of regret sublinearly, you still need to be like bounding it against some class instead of in general, right? Like,
yeah, I guess you have to be able to refuse to take gambles on like super hard computational questions. That's true. Like if someone, I can't be penalized for not knowing the 1000th digit of pi. But yeah.
Yeah, and so then we have to come up with some like way in which we decide what questions we're allowed to refuse versus what questions we're not allowed to refuse, which it sounds like you're like trying to incorporate computational complexity into that. I would also probably incorporate description complexity into that.
Which is implicitly inside of the prior, like when we construct logical induction, it just already have like this complexities involved.
Right, like in logical induction, we're dealing with computational complexity by bounding the complexity class for the traders. And then we're dealing with description complexity by traders with higher description complexity have lower weight.
Yeah, okay. Actually, this does make some sense. I do still have the doubt that I'm not. It sounds like what you're trying to say, sort of like optimality against a class of experts and this polynomial time experts, and that kind of optimality argument really only goes through if you're also a polynomial time. Otherwise, it's not so clear what it means, right?
I agree that best in class is nice. Like if you can have a polytime algorithm that is optimal versus other polytime. But if that can't be achieved, I don't agree that it's just like meaningless to have some kind of a guarantee against polytime traders, even if you yourself are not polytime.
It's not not meaningless, but it's not necessarily like a good optimality argument for logical induction. Like it doesn't rule out there could well be some other approach that's more normative, unless you can say that you have this kind of best in class property.
Yeah, that's true. But then it would also
sorry
be
to add this, but
yeah.
Do the other people have some questions or general thoughts or feedback for us? Okay, then I guess yeah, it's a bit late here, so I'll probably head out.
Okay,
Bye-bye.
well, thanks for doing a nice job hosting, Norman.
Thank you, Norman.
And what's the meeting time next week? Do we have to discuss this now?
Oh,
I assume the same.
yeah, I think the same time.
Same as this time, or the
But I think
time
we
with
don't
Linda.
have any particular agenda next week. So I think next week will be more of a open discussion, I guess. Maybe we'll be like planning the coming weeks.
But it's not this time, right? It's half an hour earlier. I just wanted to mention this because like
Oh, right,
I
right,
thought
right.
probably people who stayed here will.
Right. So for the the presentations started at a certain time, depending on your time zone. But we meet 1/2 hour earlier to have like a group discussion before the presentations begin. So next week will be 1/2 hour earlier than when the presentations began this week is when we'll actually start. Yeah.
By the way, can I just say I'd be keen if the meeting could be made any earlier, but I understand people are in many different time zones. It's just this is quite late for me, but maybe we can. I'm sure I could probably arrange meetings with other people at different times as well, like additional meetings. But yeah, just wanted to put that out there.
Yep, makes sense. I think it's pretty hard at present, but like, yeah, as the constellation of people involved changes, we can like figure out different meeting times that might make sense.
Ben,
How about Ben? You just show up one more time next week, and we can discuss the any new meeting time next week with you.
Yeah.
Yeah, sure.
Yes.
I don't mind doing that. Sorry, what were you going to say, Paul?
I was going to say, I'm going to put in a guess that you're in Australia from a combination of accent and the fact that it's getting very late for you.
Yes, good guess.
Yeah. If I'm not sure what Norman's plans are for the next few weeks, but you may want to coordinate with him directly. We actually had this problem during our AISC track where like we have Roman, well, not to give like tons and tons of information, but we have Roman in Eastern Europe, we have Hannah in Central Europe, we have Norman in China, and we have me and Abram in East US. So we had a lot of trouble trying to find a time for all of us to meet, especially since without me or Abram, like if you remove me and Abram from the scheduling constraints, now it suddenly makes a lot of sense to meet at something like, I don't know, 6 a.m. UTC. Right? That's a perfectly reasonable time for you and Norman and Roman to meet. It would make no sense at all for me and Abram, because that's 2 a.m. for us.
Yeah, no worries. That makes sense. But yeah, I think I can come at this time at least next week, especially if we're starting half an hour earlier, and then I'm sure we can discuss like future arrangements. I guess I think at one point you guys had like 2 meetings going on, like 2 kind of regular times, the different time zones and stuff. Or like co-working or something. But
there was a co-working thing. So
yeah,
maybe you can figure something like that out.
Yeah, sure. Sounds good.
Oh, okay. I'll discuss with you, Ben.
Yeah, sure thing.
Cool. Well, thanks everybody for coming. I guess we'll close up here.
Yeah, thanks everyone.
Thank you all for
Thanks
coming.
everyone for coming.
Hopefully I'll talk to you soon.
Yep. Take care.